All right, here's the video on assignment 24. Exponential models is, I guess, what I would title this homework. Okay, here we have a population growth model. Okay, a certain species of bird is introduced 25 years ago. Okay, biologists observe that the population doubles every 10 years. All right, and that right now, after 25 years, the population is 22,000. So let's try and write a model that can describe this scenario. Well, the population is doubling. The population is doubling. So whatever the previous population was, if I multiply it by 2, it is doubled, and it is now the new population. Okay. And they said that it doubles every 10 years. Okay. So I would say that 2 to the t over 10 is a reasonably good model for this situation, because once t reaches 10, then you've had a multiplication by 2. Now what I'll need to do is multiply this by the initial population. So we'll multiply it by p sub 0. The 0 meaning it's the initial population. And that this would be the population at time t. And they told us that that right now, after 25 years, then the population after 25 years would be 22,000. So then it must be the case that p sub 0 times 2 to the 25 over 10, which is just 2.5, is equal to 22,000. All right, well, I'll get out my calculator here and say 22,000 divided by 2 to the power of 2.5 that this equation tells us that p sub 0 was approximately 3889.087. And if I round to the nearest whole number, then it'd just be 3889. If I estimate the bird population 4 years from now, then that would be when t is 29. So my model, now that I know what p0 is, being 3889 times 2 to the t over 10, well, if t is 29 and it's over 10, then you just have 2.9. This is the population after 29 years. So 3889 times 2 to the power of 2.9, I get that this is 29,000 and 28.52 and so on. And I would need to round it to the nearest whole number, so I'd be getting 29,029. And then they want a graph of the situation. So I guess I'll look at, you know, where the curve started at time 0. And it can't be either of these first two up here because they start way too high. So it's one of these two down here. And I'll just pick one other number, like when t was 25, and see if that gives me 22,000. And so sure does look like it's this curve, because at 25 over here on this one, it's way above 22,000. Okay, next question is another population growth model. We have a certain species of fish has a relative growth rate of 1.6% per year. Okay. It was estimated in 2010 that the population was 12 million. And I'm just writing that down. Find an exponential model for the population some t number of years after 2010. Now this has to be an exponential model because it didn't say something like the population doubles after some number of years. It doesn't say that it triples, or that half of them die off every some number of years. We just have this continuous rate of growth. So we are able to the fish don't wait around until the 2-year mark to reproduce. Of course, that somewhat contradicts what happened in the previous problem, where it said that they double every 10 years. But it's not like those birds were waiting around for the 10-year mark and then suddenly there was twice as many of them. It was going on the whole time. Anyway, let's just write the model and I'll try and show you what I'm talking about. So, this is 12 million. This is 12 million. And if t is 0, then e to the 0 is just 1, so you would have 12 million for your population. Oh, they want the model to be in millions, so I don't need a 10 to the 6 there, we just need 12. Then it would just say the answer. So if this is a function n of t, then n of 0 is 12, indicating that there's 12 million fish. Okay, and I guess that's the answer to part 1. N of t is equal to 12 e to the power 0.016 t. estimate the fish population 5 years later. So that will be what I get when t is 5. So n of 5 would be 12 times e to the 0.8. Or, I'm sorry, 12 times e to the 0.08. And I get 12.999444481. And rounding to 3 decimal places would just be 12.999. After how many years will the fish population reach 16 million? Okay, so we would like to find the value of t that causes n of t to be 16 million. So 16 needs to be equal to 12 e to the 0.016 t. Then 16 over 12 is 4/3. So 4/3 equals e to the 0.016 t. And if I take a natural log on both sides, then we'd have that the natural log of 4/3 is equal to 0.016 t. In which case t is equal to the natural log of 4/3 divided by 0.016. And I get 17.9, that's not a 9, 17.9801 years. They want it rounded to 1 decimal place, and so our answer would just be 18. If I'm to now sketch a graph of the fish population, then I'm going to look at where does it start. It has to start at 12 million. So it can't be this one over here, and it's neither of these because it's not shrinking, so I'm done. It's this one. Another population growth model. We have a certain, oh, I forgot to say, so why was this one done with an exponential growth model? Well, it's because they presented it as a percentage of growth every year, and the fish are reproducing. I mean, wait, don't fish only reproduce certain times of the year? If I ignore that train of thought and just assume that they're reproducing all the time, like bacteria, then you would need to model it with exponential growth. However, 12 times e to the 0.016 t is the same thing as 12 times this number to the power of t. And that number, let's see, that number is approximately 1.016128 blah 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 to the power of t. So it would be like saying, oh well, heck, I could have done that. Look, this exactly says, I should have realized that even without a calculator. This exactly says that there is a 1.6% growth every year. Right? I mean, let t be 1. Then this amounts to the statement that then what it's saying is that it's 12 times 1 plus 0.016. And let me just ignore the rest of the digits. So you would have, if I distribute the 12, it would be the population I started with plus 0.016% more than what I started with. Anyhow, now we have this another population model. A certain city had a population of 191,000, okay, and the observed doubling time is 19 years. Okay, so then the model would just be, I have to have 191,000 to start with, and since it's doubling, my exponential base is 2, and then it's t over 19, because once t becomes 19, it'd be 2 to the power of 1, and that would mean it's being multiplied by 2. Okay, super. Oh, look at this. Find an exponential model for the population. Some number of, how do I hide this thing? Okay. Find an exponential model for the population t many years after 2014. Okay, dokie. Super. It's the same model, except for I would need to incorporate just that base e. Right? 2 to the power of 1 over 19, it has got to equal e to some k. Or they want to use r, sorry. R for rate. And they've told me to round my rate to 4 decimal places, so. How about we do a log base 2? Or excuse me, a natural log on both sides. Then 1 over 19 natural log of 2 to 4 decimal places is 0.036 when you round it. So this would be pretty much identical to 191,000 e to the 0.0365 t. And then I'm giving it to you as a rate of growth instead of the time between doublings. It's 191,000 e to the power of 0.0365 t. Sketch a graph of the population at times t. Well, when t is 0, it's 191,000, so it can't be this one, and it can't be this one. So it's either of these two on the left. And after 19 years, it needs to double. So then that y value right there is a lot more than double 191,000. Therefore, it must be this one. Another, are these all population growth? No, there's a radioactive decay, cooling, concentration. Okay, so another population growth. A culture starts with 8,900 bacteria. After 1 hour, the count is 10,000. And they want us to have a function where t is measured in hours, round the r value to 3 decimal places. Okay. So I'm starting off with 8,900 bacteria, and for whatever r is, when t is 1, there's 10,000 bacteria. Consequently, e to the r would be 10,000 over 8,900, which is just 100 over 89, and in turn r would be the natural log of 100 over 89, and that number to 4 decimal places is approximately 0.1165. Then my model should be 8,900 e to the 0.1165 t. Find the number of bacteria after 2 hours. Okay, that's where I'm gonna compute n of 2, right? So n of 2 is 8,900 times e to the times 2 of that. So you'd get e to the 0.233 0. And that number is 26.24% more than what you started with. Such that the total number of bacteria would be 11,235. Oh, round your answer to the nearest 100. So that's 11,200. And it also said to round this to 3 decimal places, so this should be 0.117. Well, that means I need to kind of go back over here and fix that. So let's see, e to the power of 0.117 or I mean 0.117 times 2 and then e to that power times 8,900 is 11,246, so still the same. All right, after how many hours will the number of bacteria double? Well, our model is 8,900 e to the 0.117t. If I double 8,900, it would be 17,800. So you need to solve this equation for t. It would just say that 2 is e to the 0.117t, like 2 to the 1 power, a doubling, right? And I take a natural log on both sides, so that the natural log of 2 is 0.117t, in which case t is the natural log of 2 divided by 0.117, which would approximately be 5.924. And they want it rounded to 1 decimal place, so just 5.9. The half-life of radium is 1,600 years. Suppose we have a 28 milligram sample. Find a function that models the mass remaining after t many years. So the half-life is 1,600 years, so it would have to involve a 2 to the minus t over 1,600. I can multiply this number by however much I'm starting with, and it would describe the amount that I would have after t many years. I would have this many milligrams after t many years. Well, I'd have this much radium-226. It would convert it to something else. Okay, so there's my model that does with the half-life, and this is a half-life because the minus makes it decay, or if you like, this is the same thing as 28 times 1/2 to the t over 1,600. It's like once t gets to be 1,600, then it's being multiplied by 1/2. And now they want the exponential model. And we want the exponential model because the radium is decaying on a continuous basis. It doesn't wait 1,600 years and then suddenly half of it's gone. Even though this is a continuous function, people would think about it in a discrete manner. if you were to graph this thing and then graph the exponential model I'm about to write, they would be the same graph. All we need to do is figure out where does 1/2 to the power of 1 over 1600, that this would equal some e to the minus r. Or instead of doing it like this, I'll say 2 to the minus 1 over 1600 equals e to the minus r. Because then the negatives aren't going to do anything, right? Just like how if I had 1 over a equaled 1 over b, then this would, a to the x and b to the y, then this is identical to a to the minus x equals b to the minus y. But this equation right here was, it was an equation, they were equal, so you already knew that a to the x equaled b to the y. And the minuses aren't doing anything. So it amounts to me solving this equation. Or if I just left them, you'll see how they fall out anyways. So take a natural log on both sides. Then you'd have minus 1 over 1600 natural log of 2 equals to minus r. Multiply both sides by a -1. Or just, multiply both sides by -1 and you have it solved for r. So the negatives had no role. Anyways, so natural log of 2 divided by 1600. Then this rate is 0.00043332. They want it to 6 decimal places, so there we are. My model would be 28 times e to the minus 0.00433t. So this is 28 times 2 to the power of negative t over 1600. And this one was 28 e to the power of minus 0.000433 t. How much of the sample will remain after 3,500 years? Okay, so the mass after 3,500 years would be equal to 28 e to the minus 0.000433 times 3,500. All right, so that exponent becomes a negative 1.5155, And so you'd have 6.15155 milligrams of radium-226 left in your sample. It is a mistake to think that it should just say how much of the sample will remain. If you have a rock of this stuff, that rock is going to weigh about the same that it did, depending on the sensitivity of your scale. But a majority of it will no longer be this element. It will have decayed into a different element. I think radium decays into lead. Anyways, so how much of the sample will still be radium-226? After 3,500 years, there would be 6.2 milligrams left. After how many years will only 16 milligrams of radium-226 remain in the sample? Round your answer to 1 decimal place. So now I'm curious to solve the equation for T whenever the left side says 16. Well, then you know the drill. 16 over 28 is equal to e to that power. But since it's e to that power, I'm going to immediately take the natural log on both sides and just be left with that exponent. And divide both sides by that rate. So the natural log of 16 divided by 28, which reduces, but I don't care. I get a number. It's negative. It should be negative because 16 over 28 is less than 1. And then I'll divide it by negative 0.000433. And I get that T is 1,292.4 years. I would have also liked if they had said precisely 16 milligrams. So 1,292.4. $250 milligrams of a radioactive element decays to 180 milligrams in 12 hours. Find the half-life of the element. That is a substantially radioactive element. Unobtainium, whatever. I don't know. I don't even know if that's a real element. But, I mean, that's like incredibly radioactive. So you are left with 180 milligrams whenever you started with 250 milligrams, but it decayed at some rate in the span of 12 hours to be only 180 milligrams of that substance. So 18 over 25 is e to the minus r times 12, but you can take a natural log on both sides, and it would be equal to e to the minus 12 times r, but I would be dividing by minus 12 and just be left with r. So the natural log of 18 over 25 is this here number. It's negative because 18 over 25 is less than 1. And then I'll divide by negative 12. And I get that my rate is approximately 0.0274. They don't really tell me how many digits to keep here for this rate. I think they've handled that problem by having us round our answer just to the nearest hour. So 4 digits ought to do it. Then my model is, come on now, my model is 250 e to the minus 0.0274 times 12, or times t. Find the half-life of the element. Ooh. So we are curious then, where does this thing equal to 125? Because if I am studying the equation, 125 equals to 250 e to the minus 0.0274 times t, then the number on the left is half of what I started with. And if I can solve for t, if I can solve for t, then I would have the time t that resulted in only half of the original element remaining. If I divide both sides, so in the course of solving this equation, divide both sides by 250, you get 1/2 on the left. It's just a matter of when does this portion right here equal to 1/2, no matter what you started with. Because whatever you started with, it would need to be multiplied by 1/2. And so we're really curious about where does this thing equal to 1/2. And like I said before, 2 to the minus 1. I won't even do that. So natural log of 1/2 is a negative number. It equals a minus 0.0274 t. Divide both sides by this other negative number and you'll get a positive number. So t is the natural log of 1/2, which is just minus the natural log of 2. If you've been keeping up with your logarithm properties. So the natural log of 1/2 divided by minus 0.0274. And I get this is approximately 25.29 hours. So to the nearest hour is just 25. This exercise uses Newton's law of cooling. Don't particularly remember that from physics class. But fortunately, they've given us the formula here. Got a hot bowl of soup at the dinner party. We can model the rate at which it cools off with this here formula. Evidently, the room temperature is 60. Because as t goes to infinity, this part would go to 0. And it would reach room temperature when t goes, it approaches room temperature as t goes to infinity. So it must be 60 degrees in that room where the dinner party is held, or at least where the soup is served. And what is the initial temperature of the soup? Well, when t is 0, if t is 0, then this is 1. it says that the soup is 131 degrees hotter than the room. So the soup is 191 degrees. What is the temperature after 10 minutes? Well, I would need to compute 60 plus 131 e to the minus 0.05 times 10. Which is just 60 plus 131 e to the minus 0.5. E to the minus 0.5, let's see. This number right here is approximately 0.6065. So it's telling me that the temperature, that this 131 degrees needs to be 60.65% of what it, I'm going to take 60% of 131 and then add it to the room temperature, and that's the temperature of the soup. I do all this and I get 139.4555, and so on. They want it rounded to one decimal place, so 139.5. After how long will the temperature be 100 degrees Fahrenheit? All right. So now we are curious about just looking at our model without a time plugged in for t and putting this equal to 100. So that's the same thing as where 131 e to the minus 0.05 t is equal to 40, which is the same thing as where e to the minus 0.05 t is equal to 40 over 131. And if I take a natural log on both sides, then divide by minus 0.05, t would equal to the natural log of 40 over 131 divided by minus 0.05. Both of those, the numerator and the denominator there, are negative numbers, so we'll get a positive t. The natural log of 40 over 131 is like negative 1.186, and then divided by negative 0.05, and I get 23.726. Rounded to the nearest whole number is 24 minutes. 24 minutes. The hydrogen ion concentration of a sample of each substance is given. Calculate the pH of the substance. Well, the pH is calculated by just taking the negative of the log, the common log. So the pH is minus log of the hydrogen ion concentration. For lemon juice, they told us that the hydrogen ion concentration was 5 times 10 to the minus 3. And for tomato juice, it was 3.2 times 10 to the minus 4. Excuse me. And for hominy, which is lie, evidently, did not know that. It's pretty extreme here. So the hydrogen ion concentration is 3.9 times 10 to the minus 13. That was just the information that they gave me. So, in turn, the pH of the lemon juice is minus log times 5 to the 5 times 10 to the power of minus 3. But that minus can come up here, and I can save a step in my calculation by just saying log of 5 times 10 cubed, which is just the log of 5,000. Whatever number that is, that's the pH of lemon juice, which is acidic, if you didn't know. Tomato juice, less acidic, more basic, less acidic. It has a higher pH than a lemon juice. And so we'd have the log of 32,000. Or actually, wait a minute, I'm screwing up, aren't I? If I back up here, I just realized something. Yes, it's minus log of 5 times 10 to the minus 3, but when that minus is brought up into, if I want to say that this is log of, if I want to bring that negative up into the exponent, then it would be 1,000 over 5, not 5,000. Sorry. Right, because it would be log of 5 to the minus 1 times 10 cubed. So it's 1,000 over 5, which is 200. And for the tomato juice, you'd have the log of 10,000 over 3.2. Or however you want to type it in. If you want to type it in minus log 3.2 times 10 to the negative 4, be my guest. But it's not going to make a difference. They're all the same. Minus log 3.2 times 10 to the minus 4. I think my way has just less buttons to press. Here you'd have, now here I would keep my exponent because 10 to the minus 13, isn't that like 1 over 10 trillion? I mean, it's more than a million. A billion is 1,000 million, and a trillion is a million, and then that would be 10 to the 13 is 10 trillion. So you could compute this as the log of 10 trillion divided by 3.9. They'll all get it done. Okay, so let's get some numbers. Log of 200 is 2.3. That's very low pH. It's acidic. for tomato juice, we'd have log of 10,000 over 3.2. You get 3.49. Or rounded to one decimal place would be 3.5. But it's still acidic because it's not neutral. Neutral, I think, is 7. However, this here hominy, lye, would be very, very basic. It's on the far other end of the spectrum. So I'll take log of 10 to the power. So here's even another way we can look at this that would be useful for your understanding of what's happening with the log. So back to the lemon juice, minus log of 5 times 10 to the minus 3. Then logarithms map multiplication to addition. So you'd have minus log 5 minus log 10 to the minus 3. But then this minus, in fact, that minus 3 can just come down out front, and you'd have minus log 5 plus 3. Why is it plus 3? Because log of 10 is 1. So this exponent amounts to us picking an integer and then deducting away this amount to figure out what the pH is. And that amount there would be a minus 0.7. Which is how I got that this was 2.3. So then, consequently, for the lye, let's have a look. We'd have minus log of 3.9 times 10 to the minus 13. But logarithm maps multiplication to addition, so this is minus log 3.9 plus 13. So we're going to go way out to the number 13 and then take away this much. And conceivably, when you're calculating pH, you could just jump straight to there every time, right? If I had a substance whose hydrogen ion concentration was N times 10 to the M or minus M, then the pH of that substance would be equal to M minus log N. It's all the same. In fact, this seems easier, but whatever. Let's see, 13 minus log of 3.9, I get 12.4. That's awfully basic. All right, let's make sure I know what I'm talking about. Sure enough. Finally, they've given us the pH. We need to find the hydrogen ion concentration. Tomatoes and crackers. That's funny. So Terrific. The pH of tomatoes is 4.1. So 4.1 needs to equal minus log of the hydrogen ion concentration. Ten to the power of 4.1 or I guess let me do it like this. Minus 4.1 is log of this number we are looking for. So 10 to the minus 4.1 is the number of hydrogen ions. Not the number, but the concentration. Okay, well, you just need to present this in scientific notation, right? So that number is really what do I want to say? I'm thinking about 10 to the power of 0.9 times 10 to the minus 5. Because if you add those together, you'll get minus 4.1, and then this number right here, is it between 1 and 10? Sure enough. So 10 to the power of 0.9 is 7.94. And they want everything to 1 decimal place, so this would be 7.9 times 10 to the minus 5. Okay, and final question for crackers. pH is 7.2. So 7.2 has to equal minus log of the hydrogen ion concentration. And so that means that minus 7.2 is just log of the hydrogen ion concentration, in which case 10 to the power of minus 7.2 is the hydrogen ion concentration. But this is really 10 to the power of 0.8 times 10 to the minus 8. Because if you add minus 8 and 0.8, you get negative 7.2. 10 to the 0.8 is certainly less than 10 and will be bigger than 1. So I get 6.3 times 10 to the minus 8. I knew that 10 to the 0.8 had to be less than 10 because 0.8 is less than 1. So 10 to the 0.8 is clearly less than 10. Why is it greater than or equal to 1? Well, let's put a bound on that. So I want 10 to some exponent to be bigger than or equal to 1. Or I guess I'm just curious, where does this happen, right? Well, that would be when t is 0. So as long as your exponent there is a positive number between 0 and 1, excuse me, as long as it is a positive number less than 1, that's not even, it can't be negative, a non-negative number less than 1. a non-negative number less than 1, then you're guaranteed that 10 to that number is between 1 and 10. So 6.3 times 10 to the minus 8. It's nearly, what's the word for, it's nearly, right halfway between acidic and basic, neutral. It's nearly neutral. Crackers. All right, it's an hour-long video. Sorry about that. Maybe you work the assignment along with me, in which case you'll be done shortly. Thanks for watching.